Hello, I'm Cosimo della Santina, and I'm going to present the work that we did together with Davide Calzolari, Alessandro Massimo Giordano, and Albu-Scheffer about eigenmanifolds and their actuation. So the goal of this work is to characterize all eigenmanifolds preserving actions, which stated like this, I can imagine is a pretty confusing goal. So I want to take a few minutes to explain what this means and why this is important. And we start from the good old natural inspiration and to the fact that all animals are able to exploit the natural dynamics to perform oscillatory motions in an efficient and an effective way. So we would like to obtain similar performance in periodic tasks with artificial systems, like, for example, robots. And among all robots, this is particularly relevant for soft robots, so mechanical system with elastic elements embedded into them, because this makes them especially suited for performing oscillatory tasks. However, the theory is developed for generic mechanical systems. The framework that we propose is called controlling eigenmanifolds, and it's based on a two-step process. The first one is to analyze what the robot can do well. And the second is to close a loop that can exploit the natural capabilities of the robot and help the robot express them. This framework has been laid down by 3 papers that we published recently, and 2 of them are already discussed and at the link that you can find behind these QR codes. And this talk is about the 3rd paper. But let me first give you some basic details about the stuff that we presented before, so that I can then get more into the technicalities of the new results. Now, what are eigenmanifolds? Eigenmanifolds are a direct extension of eigenspaces to the nonlinear domain. So as eigenspaces are a flat collection of infinite amount of periodic orbits, regular periodic orbits, the same eigenmanifolds are an infinite collection of nonlinear oscillations, which are self-similar. Just to give you a visual representation of what we mean, is that if we take a KUKA lightweight robot and we just add parallel springs just for the fun of it, the open loop evolution would be some messy quasi-chaotic behavior as the one that you have here. While, however, we can identify 7 eigenmanifolds, and here we are just showing one evolution associated to each of the eigenmanifolds. And you can see that these evolutions are regular oscillatory behaviors that you can imagine to actually use for some practical application. And these are completely open loop evolutions. So now that we have this definition and we also have a way to evaluate these eigenmanifolds, how do we use them for control? This is where the second step comes into place. And our first step, the first block was to introduce in this paper, and the idea is just to say, okay, outside the eigenmanifolds, the behavior is mass evolution. On the eigenmanifold, we have a regular oscillation. Let's just make the eigenmanifold an attractor for our robot or for our mechanical system by means of feedback control. And already a PD-like action in most cases is sufficient to achieve this goal, and the result is pretty nice. If you initialize your robot somewhere and then you wait for the feedback controller to attract the state towards the eigenmanifolds, at steady state you get an hyper-efficient oscillations, which is very regular. And again, you can think of using it for practical application. I want to stress, and when I say hyper-efficient, I mean that the control action is going exactly to 0, and that the oscillation that you see is completely autonomous. But is this sufficient to solve the control problem? The answer is no. And let's look at a simple example to understand that. So double pendulum, some parallel elasticity. As I said before, an eigenmanifold is a collection of an infinite amount of oscillations. And you have one oscillation for each energy level, and you can think about this as having oscillation with different amplitudes, with increasing amplitudes. Stabilizing eigenmanifold is thus clearly not enough because our system will end up evolving on one of these modes for a specific selected eigenmanifolds. But I want to be able to specify which of these modes, so which amplitude is the oscillations, or more specifically, which is the energy of our oscillation. So we need to think of another loop that regulates the energy. So we can now look back at the initial picture and hopefully now try to understand better what is going on there. So we have our eigenmanifolds, and we have several energy shells, so infinite amount of energy shells, and the intersection between the energy shells and the eigenmanifolds are our nonlinear modes. The question that we want to answer is therefore, how can we transit from one mode to another? So how we can change the energy? And is this even possible for any given mechanical system under the condition in which I always remain on the eigenmanifold? In the paper, we show that there is actually a pretty simple condition that we can look at to see if we can or not achieve this goal. And the idea is that we look at the eigenmanifold, and then we look at the configuration space. The eigenmanifold lives in the state space, so position plus velocity. We look at the configuration space, and we just do a very simple standard projection of the eigenmanifold in configuration space, and then we look how the modes looks like in this projection. And there are three possible behaviors that are qualitatively different, and they are the case in which all the trajectory create a one-dimensional manifold, the case in which the trajectories are spread but they self-intersect, and then there is one extreme case in which you don't have the trajectory are so spread apart that they do not even self-intersect. So we start from this latest case because it's the simpler to address. The answer is quite simply that there is no way to transition from one mode to another without leaving the eigenmanifold in this case. And to show that unfortunately this is not an uncommon case, this is an example of a mechanical system that has this behavior. Let's now look at the other end of the spectrum, so the case in which all these, we have all these symmetries, all this projection, and create a one-dimensional manifold, so a line in configuration space. And in that case, we proved that we can always quite easily create a manifold preserving action. So a control action that do not push you away from the manifold. And the key ingredient here is this nu of x, which is the tangent direction to this projection. And this is the M is the inertia matrix. And what is important here is that you can plug there whatever action tau star in R, and this is always going to be a manifold preserving action. So we can exploit this fact to create some closed loop energy regulations. And the nice thing here is that this energy regulation does not explicitly include this nu. And the trick that we use is that the derivative is always a scaled version of this nu. And this is an example of a mechanical system being excited using this technique. And you see that after a few seconds, this robot starts oscillating again with in an open loop evolution, so null energy consumption in steady state. Let's now look at the middle ground, so the case in which we have modes intersecting, but not forming a one-dimensional manifold. And this is, for example, the case of the double pendulum with parallel elasticity that we looked at a few minutes ago. You can see on the right a collection of these eigenmodes, and you can see here on the bottom left an area in which all these trajectories intersect within each other. And we developed some theory and some algorithm to analyze this case. We don't have times here for detail. Of course, I'm happy to discuss offline if you're interested. I'm just going to discuss the K idea here. And you can think, for example, of taking two modes for two energy level, A1 and A3, and you want to move from one to the other. And the way in which you do that is that you have first to identify where these two lines intersect, and then you have just to create an impulsive control action, so a direct delta, that instantaneously change the direction of the velocity from the one that keeps you on one mode to the one that moves you on the other modes. And we call this change in the state a jump. So what about the more complex case in which you maybe want to move on E2, but E1 from E1, but E1 and E2 do not intersect? It's pretty simple, at least in principle again. You can just use E3 that intersect both of them as a sort of a bridge, and then you just do a double jumping. So first from E1 to E3, and then from E3 to E2. And you can see here in the simulation what happens if you want to do a similar thing for the double pendulum. And you can see here two jumps, and you see that x does not change instantaneously, but of course what changes is the velocity, and you can see a quite different behavior between jumps. And it's again very important to stress that the evolutions between the jumps are completely open loop, and they are regular oscillations that are expression of the natural dynamics of the robot. So in this talk, we show how we can kind of complete our framework, at least the grounds of this framework, by giving us the possibility of varying the amplitude of oscillations in a way that does not disturb the eigenmanifold stabilization that we proposed in our previous work. And we show that this is possible whenever the projection in configuration space of our eigenmanifolds is either one-dimensional or has trajectories that self-intersect. Thank you for your attention, and I remain more than open to discuss whatever question you may have, either after the talk, in the main conference, or via email. Have a nice day.